Hey everyone, Mr. Shatter here to talk about differential equations. Objectives of this video to formally define differential equations, to introduce slope fields, and to use slope fields to predict information about solutions to differential equations, which you may not have otherwise been able to know. Some differential equations are not solvable for us, and slope fields will help us predict information about those solutions. Step 1, defining formally differential equations. An equation involving a derivative is called a differential equation. So this is an equation you're going to be given of the form, dy dx is equal to. So you're going to be given the derivative, and then we're going to be asked to find information about its solution, or its antiderivative evaluated at a point, if you will. The order of a differential equation is the order of the highest derivative involved. This is basically just saying, like, you've got second derivatives, third derivatives, fourth derivatives. So whichever one that, I give you to start with, that's what we consider its order. So like, if it's a second derivative, we consider it to be a second order derivative function. Most of the time, we'd just be working with dy dx. So its first derivative, that would be the highest order. So example 1, solving a differential equation. This problem says find all functions y that satisfies the differential dy dx equals secant squared x plus 2x plus 5. It does say all functions because remember there are actually an infinite number of them that have that same derivative. And let's go ahead and just pick them or create them. So dy dx is secant squared x. The antiderivative of secant squared x is tan x. And then 2x, if you anti-differentiate, would give you x squared, and 5 would give you 5x. And then we add this plus c, because of course it could be any value of c in any function that has a constant at the end of it. As long as it's of this form, we'll have the differential equation listed there. Sometimes you're given a point, and you want to then find the particular solution of the differential. So this one's dy dx equals e to the x minus 6x squared. So obviously if you go backwards and use antiderivatives, antiderivative e to the x is e to the x. Antiderivative of negative 6x squared would be negative 6x cubed over 3, which would just simplify to a 2 out front. So it would be negative 2x cubed. But this one, it gives you the point, 1, 0. So when we do our plus c here, you can actually find this value of c by setting the y equal to 0. The exponential e to the 1 is just e, minus 2 times 1 cubed is 2, plus c. So then if you just move the e and the 2 over, you get c is equal to 2 minus e. And so therefore the original equation, the actual particular solution, would have been e to the x minus 2x cubed plus 2 minus e. And this is now the singular solution to the differential, not the family of functions or the family of solutions. So what happens if you get to something that looks like this? Very common differential equation, 8x over y. We have no idea what the solution to this equation would look like. We cannot find it at this time. You need more knowledge to find it. But this is where slope fields come in. So slope fields are going to be able to be constructed to give us information on what this solution to this differential would look like, even though we can't actually solve it. So a slope field uses what's called local linearity, which are just basically linear line segments, to construct a graph of possible solutions to differential equations, even if that differential equation is not solvable. Let me give you a really easy example to kind of wrap your head around, and then we'll get into some more difficult ones. Let's consider dy dx is cosine x. So the differential I gave you was cosine. Now we know the solution to the differential equation is sine x plus c, right? Where it's any value of c. It could be plus 1, plus 2, plus 3. So these blue curves are basically just a bunch of sine x curves translated up and down depending on what the value of c would be. So if we use the dy dx to be cosine x, so that's actually our slope, okay? We can actually build a very similar picture to this using information about the derivative, okay? So moving forward, let's consider dy dx to be cosine x, all right? So let's go ahead and one step at a time, figure out some scenarios. So scenario number 1, if dy dx is cosine x, at any point 0, y, the differential gives you an answer of 1. Now this is because this dy dx differential doesn't contain y in it. It only contains x. And we know that cosine of 0 is equal to 1, right? So it doesn't matter what value it is you put in for y here. If you plug a 0 into x, this differential equation will give you 1. So what we do is we put little line segments that have a slope of 1 up and down that line right there, y equals 0, or x equals 0 rather. And so you just kind of put them down and you space them out appropriately. Don't worry too much about the scale right now, but you just kind of put those line segments in there. You might be wondering too, why can we do this? And some differentials look like, x plus y, and they have x's and y's, in which case now it complicates things. This differential only has a single variable, x, so that's why we can kind of say for any value of y, this slope is 1. Okay, now if you plug in a pi, you get -1 as an answer, right? Cosine of pi is -1. And again, it is not dependent on the value of y, because there's no y here. So we just go and we put little slopes, little -1 slopes here, up and down these values, kind of adding it to our picture. We're building the solution to this differential. Another thing you could say is the slope is equal to 0 at odd multiples of pi over 2. So pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. And that literally looks like a little flat line, because the slope of a horizontal line is equal to 0. So we just put those at appropriate intervals of odd multiples of pi over 2. And last but certainly not least, we know that the slope is equal to 1 at plus or minus 2 pi. So we know that cosine of 2 pi and cosine of pi is equal to 1, because that's just cosine basically finishing its first period, and it repeats itself and it starts back at 1 again. And so we can add these little line segments of 1 at -2 pi and positive 2 pi. And you can almost see the picture, right? You can almost see, I'll use a highlighter, the general pattern for this is like little sine curves, okay? And what we've done is we've essentially created multiple sine curves for this. And the slope field together, pieced together, are these solutions, as the sine x plus 1, sine x plus 2, sine x minus 1, sine x minus 2. So without even solving the differential, we're able to kind of piece together what its solution would look like using lots of little linear line segments. Let's try a matching exercise. In this activity, we see two slope fields. One of them links up to dy dx equals x plus y, and the other links up to dy dx equals x minus y. The easiest place to start, especially if you have a slope field that contains, or a differential that contains two variables, is to set the differential equal to 0. So let's say we start with this one, okay? If we set dy dx equal to 0, we'd have 0 equals x plus y. And if we minused over one of the variables, I'll minus over the x, we get y equals negative x. Along this line, this means that the slope should be 0. So along the line y equals negative x, we should see a slope of 0. Or, using linear functions, we should see horizontal lines, right? So let's examine the slope fields. It looks like the left slope field has this, right? Right here, these horizontal lines along the line y equals negative x indicate a slope of 0. And that's exactly what we needed for this left one. So we can assume that dy dx is equal to x plus y. That links up to this one, which means that this one should be x minus y. And it's really easy to tell, if you take your differential right here, dy dx equals x minus y, and we set it equal to 0, and you solve by adding y, you get y equals x. And that is where you should see a slope of 0. And if you examine closely, that's totally true in this right picture. So we have the proper equations. Now, one strategy you can use for slope fields, especially if they are multivariable, meaning you have x and y, and it sometimes is a little harder to see, is you can make data tables. Let's try some data tables. Let's do x, y, and what your slope would equal, and x, y, and slope. Let's test some points. Let's test 0, 0. So if we plug 0, 0 into the differential x plus y, we get a slope of 0. How about if we try 0, 1? Well, we'd get a slope of 1. It'd be 0 plus 1, right? dy dx gives you 1. 1, 1 would give you 2. 1, 2 would give you 3, 2, 1 would give you 3. Just plugging the x and the y value into dy dx, and that gives you the actual slope that this line segment, this linear line segment, should have. So let's compare that to the right one, where 0, 0 still yields 0, but 0, 1, interestingly now, gives you a slope of negative 1. So let's examine 0, 1 on the right picture. That's right here. This little red line segment that I drew. That has a slope of negative 1, but compare that to the left one, 0, 1 has a slope of positive 1. So that's a big difference. You could also check 1, 1, which interestingly enough will have a slope of 0. We already saw that up there with the highlighted line. You could try 1, 2, which would have a slope of negative 1, or 2, 1, which would have a slope of positive 1, if you plug those into the differential. So sometimes making data tables helps kind of see what's happening. The last thing is sometimes you're asked to graph a particular solution, and that's just when you take a slope field and a coordinate point of, my choosing or someone's choosing, and you sketch a general shape, kind of like this blue curve, that would pass through 2, 0, which in this case would be approximately right here. And to do this, you just follow the pattern of the slopes and sketch something that looks a little similar to the pattern, but goes through that indicated value or point.